because I think I'm getting confused between all of them and what all the tests mean, when to use what, and like what I'm actually looking at. So, Professor Bartman went over the t-test,
Yes.
which I get. He went over it in class, like t-test for dummies. And I get it. My only question now is like, what are these values? Like, what are they being called? Because, okay, so for example, when I calculate a t, right, and I do the formula, what is that called? Like, what do we say that is?
So we say that's a calculated t.
You just say calculated t.
Yeah.
Okay. And I think I'm also getting confused between the book and what they're calling it in the book. And then, so then when you get the value from the book, like the back of the book, the charts, what do you call that?
That's the t critical value.
Okay. So calculated t and the critical value.
By the way, the calculated t sometimes, especially like in the context of a t-test, we also call that a test statistics.
Yes. Okay. That's also where I was getting confused. So a test statistic is the calculated t. It's also the calculated z.
Yeah. It's
okay. That's
so,
it. Because I was like, what is the test statistic?
So, because that depends on what test you are conducting. So if you're conducting a z-test, then your calculated z is your test statistics, and if that's a t-test, then the calculated t is your test statistics. And like later on, you will learn a lot of like more tests maybe. So basically,
I hope not.
yeah, but so basically, you like use a formula to calculate something related to determine will you reject or not reject the null hypothesis, and that parameter is your test statistics.
Got it. Okay, that makes a lot more sense. So then also in relation to the t, when you so the calculated t, I know like what that represents on a curve and like where it falls, but what exactly does it mean for the sample? Like, what are we saying that in this one, for example, this calculated t is, oh wait, no, that's not it. 2.624. So like, what does that actually mean? This was the example we did in class yesterday.
Yes.
So like, is it that, and this was it was for a 2 sample t-test.
Yes.
And the calculated t came out to 2.624. So I understand that when we look at the t critical value, if it falls within this, we don't reject null, and we do reject null. But what does 2.64 mean? Does that mean it's the average? Like, I don't get that. I can't figure out what that.
So first, I'll try to start with a more easy example, which is a z-score test. I think that is more like it's easy to understand. So basically, like the rationale between those tests are pretty much very similar, but a z-score test is like the most basic one. So I think I'll start with that one.
So so before we go into this, actually,
yep.
Can we say what the difference is between the t and the z? I have no clue what it is.
So yeah, so basically there's 2 different distribution. We have a z distribution, we have a t distribution. Basically that's a curve that makes, so the area inside that curve equals 1. So there's 2 probability function, right? And by the way, the z-score test, we're just using the normal distribution. It's a bell curve. And you can draw the bell curve. It's symmetric, and the area equals 1. So basically, that's the distribution in our z-score table. The t distribution is much more difficult than the z-score distribution. And by the way, that distribution line, I guess it's like fx equals e to the power of I don't know, x to the power of negative e something. I'm not too sure about
It's
it, but
okay.
yeah, it's a complicated one. And if you want to calculate the area, you should like use the integral to find the area, and all of the distribution it comes out that their area equals 1. That's a very important attribute of distribution. So
But both of them, wait, you just said the area of a t-test is 1?
yeah, so all of this distribution curve, the area inside equals 1.
And that's for but isn't that for the z-test too?
It is. It's also the area is 1.
Okay. Okay, I just
So
want
basically,
to.
can I share my screen?
Yeah,
Maybe I
absolutely.
can, but like I think you should like make it like I cannot share my screen right
Oh,
now.
oh, oh.
Yes.
Can you do it now?
Yeah.
Uh,
Thank you.
okay.
So I'll try to. Can you see this?
Yep.
Yes. So basically, I try to draw. This is like a bell curve.
Mm-hmm.
It looks similar to this. And
Mm-hmm.
so inside this bell curve, the area equals 1. And
Mm-hmm.
in the middle, this is your z-score equals 0. Because what does that mean? Remember, what's your formula for z-score? You use x minus mu divided by standard deviation. And when
Mm-hmm.
x equals mu, it means when your sample mean equals to the population mean. So that's where lies the biggest the probability, right? So an example is like I'm choosing 1,000 coins, and
Mm-hmm.
my mu. What is my mu? It's easy to say that my mu is 500 because that's
Mm-hmm.
the population. That's a population mean, which is like 50% times 1,000. So this is a theoretical expected value. And
Right.
if, for example, I toss 1,000 coins and in reality I really find 500 heads, what does that mean? That means like I'm lying here, right in the middle. And when you
Okay.
calculate the z-score, it's really just 0 because x minus mu is 500 minus 500 is 0 divided by standard deviation. No matter what the standard deviation is, it's just 0 divided by a standard deviation. It's 0. And you're not surprised. So by this chance, I would say the probability of finding, because here, remember, our calculated z is 0. This is our calculated z, also our test statistics in this case.
Yep.
So the probability of finding a z-score greater than 0 is simply you find the area on the right of 0. And because
Okay.
this distribution is symmetric, so basically that probability is 50%.
Okay.
However, I think you have you have did a lot of those kind of calculation, those kind of practice examples. For example, I would ask you, what is the probability of finding, for example, 600 heads
Right. Yeah.
out of 1,000 toes, right? So what you're gonna do here, this is your x.
Yep.
You use x minus mu, that would
Mm-hmm.
lead to a 100, and divide it by standard deviation. And you know the standard deviation for a binomial is NPQ, right? So it's
Mm-hmm.
basically NPQ square root. Basically, it's like 1,000 uh, times a half, and then square root that. So you
Mm-hmm.
know how to calculate this. So you get a z-score. This z-score, by the way, will be very high. Will be very high. If you calculate that, I will do that. Takes a few seconds. You find it's 20.
Okay.
this is a very, very high z-score. So basically, in reality, there's no chance that you get 600 heads out of 1,000 toes. So 20 means what? So here, my z-score is 20. It's on the right.
Yep.
And my probability of finding 600 or more heads out of 1,000 toes is also like this is the area on the left side, on the right side, I'm sorry.
But the z critical value, like that's what the area is?
Yes.
Okay. So the 20 is what falls on the curve. The z-score is what falls on the curve where it falls.
Yes.
And then I know it sounds like I'm dumbing it down, but I'm also visual. So I think if I can visualize this, it'll make a lot more sense, like we're doing right now. So then when you take get the z critical value, that's what you just crossed out here. That's
the area. So basically here we don't, so in the z-score test, we don't have a critical value actually. But what you're going to do is you just go to the z table and you can find the probability and its corresponding z. For example, what I know is if you find the probability of 50%, right, you'll find a z-score which is 0. I know that for sure. By the way, what you're really gonna do is you find the probability of 5%, because that's the kind of a cutoff in many statistical tests. What does that mean? It means that is a z value. So for example, this is my z. You can maybe you can call that a critical z as well. So this is my z value that gives me an area of 5% on the right of all this distribution.
Okay.
So basically here, you have it's 5% because the whole area equals 1. So basically the area on the left is 0.05.
Okay.
Right. So basically.
Okay, go ahead.
Yeah, so basically we have two ways of rejecting the null hypothesis. The first, I have already calculated this 20. This is my calculated z. Then I find my critical z, which is maybe this z is equal to 1.96. I happen to know about this data. So basically, if I get a z-score which is higher than 1.96, then it means my z-score is on the right of my z critical value. It's on the right, no matter it's 20, it's 15, it's 12, as long as it's greater than 1.96. Then I reject the null hypothesis. Why? Because the probability of finding a z which is greater than my calculated z, is the area here. And this area is less than 5%. Because remember, 5% is all those area. This is 5%. And as long as I find a z calculated z value greater than 1.96, then I'm very sure that the probability is less than 5%. That's how I reject the null hypothesis.
Okay, so to recap, this 1.96 is based on the 5%.
Yes.
So then you calculate the z. So anything that's greater than this 1.96, you're going to reject the null hypothesis.
Yes.
So then 20 is obviously bigger than 1.96. Okay.
Yes. And again, there's another way of rejecting the null hypothesis, right? Because I find that 20, instead of calculating what is the z critical value. So for example, I didn't know this 1.96. What do I do? I just go to the z-score table and plug in z equals 20. It will give me a probability. So basically, the z-score table, as long as you have a z, you have a probability. As long as you have a probability, you have a z. So basically, at first time, I'm plugging 5%. I'm plugging the probability equals 5%. Then I find my z equals 1.96. But then another way of doing this, I plug in z equals 20. And then I get a probability instead. I plug in z equals 20, I get a probability, and that probability would be very, very, very low. And then I
Right.
compare that probability with my alpha, which is in generically 5%, and that is less than the alpha. So again, I reject my null hypothesis.
Okay. I think I'm confused by all those different ways to reject it. So the first way you reject it is because 20 is so high and you know that that's just not doable. Is that what you're saying?
Okay. So I try to make it more
No, it's
clean.
okay. It's just too many Z's.
Yeah, it's true. Basically, the way we reject the null hypothesis is because so that this is like the most, I think, like intuitively, the reason we reject the null hypothesis is the probability of null hypothesis being true is too small, right?
Mhm.
That's why we reject it. And basically, in a z-score table, I have a bell curve.
Mhm.
It doesn't seem like a bell curve. I have a bell curve, and then I have different z's. It's on the table. I have different z's.
Mhm.
Things I know is when z equals 1.96. By the way, you can check that out in the z table. When z equals 1.96, this area on the left is 5%. So
Okay.
because of like the whole area equals 1, so we can kind of use the area to uh, to uh, so basically the area is equals to the probability because everything included, the area is 1, the probability is also 1. Here, this area is 5%.
Okay.
So what you know is if you find a z-value, which is
Mhm.
greater than 1.96, if I find a z-value which equals 2, what would I
Mhm.
say? The probability of finding a z-value that is greater than 2 is the part lies here.
Yeah.
But remember, all of the area on the right of 1.96 equals 5%. So here,
Mhm.
the area here is 5% minus the area between 1.96 and 2. So that
Mhm.
would be less than 5%. That means the probability of my null hypothesis being true is less than 5%, and thus we reject it,
Okay. That makes sense.
right?
So what is the 1.96 again?
You look at the z table and you find the 5%, and then you can get 1.96. So basically in the z-score table, as long as you have a z-score, you can get its percentage.
And it's 1.96.
You can get a percentage. Because this is a normal distribution, that
Yeah.
distribution have a function. So mathematically you can calculate like the area as long as you gave me some value.
Right. So essentially, the value you get from the Z table is what you're going to use to determine if your calculated Z is too high or too small, or can be rejected or not rejected.
Yeah, because here my calculated z is 2, which is greater than 1.96.
Right. Okay.
So I reject it.
I think I got this then.
Okay, but again, what I want to say, like there is a second way, and I think you have to understand
Okay.
that. So
Mm-hmm.
the first way is I know my alpha is 5%. This is my alpha. So I plug in alpha equals 5%. I plug in this into my z table, and I find my z is 1.69, 1.96, sorry. And then my calculated 2 is greater than 1.96. So I reject it. But another way is I have my z-score. This is my calculated z-score. It's 2. And then I plug in this 2 into the z-score table. And I will find a probability which is like 4.9%.
Okay.
And that is less than our alpha. Our alpha is 5%. So again, that gives us an evidence to reject the null hypothesis.
Okay. I feel like I'm reading this table wrong now.
Yeah.
Is it hard to read this table? Like, could I actually be reading this wrong?
I don't think it's very hard to read the
I
table.
didn't think so either. So 1.96, I'm looking up a z value of 0.5.
You're looking at the z value. So you're looking at the probability. I just Googled it. So can you see this chart?
Yes.
Okay, so at z-score, you have like on the right, you have 0.00, 0.01, those things,
Yeah.
right? What you're gonna find, what's useful is 0.05. That is a percentage.
Yeah.
That is 0.05, right? So to get a 5% area, just screw down, 5%. Do you find there is z-score? Right, so for example here, when z equals 0.0,
Yep.
then I find z equals alright, here's the thing, right? So basically the probability is in the middle of the chart,
Yep.
right? So the first line, so first we look at the first horizontal. Maybe we look at the first vertical line. First vertical line says z equals 0 0.0, 0 0.1 all the way to 3.4, right? And what's in the first horizontal line is basically it gives us a second decimal place. So the first point,
Oh, I see.
yeah, if you want to locate like z equals 1.05, you will go to, so first you find z equals 1.0, and
Yep.
then you go to the column, which gives you a second decimal place of 0.05. You can find the z-score.
My God, I've been reading this fully wrong. Okay, I hate myself. I get this now.
So what? Oh, I think this graph is nice, but I don't know if I can draw on it.
And the one in the book confuses me.
Okay. Okay.
Because
So
it has like the curves on the top, but I feel like I don't actually use those.
so if you look at what is 1.96 here, 0.06, this column 0.06. I know maybe you cannot see my mouse, but I try to.
I see it. It's okay.
Okay, so this is 0.06, and then you scroll down to here 1.9. So what you find when z equals 1.96, the probability is 0.9750.
Okay.
97, 9750, I think. Yes, 0.9750.
That makes sense.
What does that mean? That means the shaded area when z equals 1.96, the shaded area have a probability or have an area of a 97.5, which means the white area is 2.5%. And if that is a two-tailed test, then you have an alpha equals 5%.
Got it.
But
if it's a one-tailed test, you're saying it's just 0.25 or 0.25?
If that's a one-tailed test, you should find like in the middle, all the way in the middle, there's a lot of numbers, and you want to find a 0.95, right? So
Right.
we want to find a 0.995, then it depends. Here you see there is a point 9495, also a 9505 in the middle,
Mhm.
in the line of z equals 1.6. If you can see that, that's basically the
Yeah.
cutoff point. There is a 9495 and a 0.9505. So basically, the cutoff point is z equals 1.64 and z equals 1.65 if that's a one-tailed test.
Okay. This makes so much more sense.
Right. So basically, what you'll find is as long as I have a percentage, I can locate a z-score. As long as I
And then,
have a z-score, I can locate the percentage. I can locate a probability. So that's why I said there's two ways to determine if I have to reject or fail to reject the null hypothesis. The first, I find this 2 is greater than 1.96. So basically, I find my calculated z is greater than the z critical value. That is an evidence to say that the area on the right of 2 is less than 5%. That's why I reject the null hypothesis. The second way is I plug in z equals 2 in that z table. In that z table, you can do everything. You just plug in z equals 2.0, and then you can find the probability. This is a made up one, but basically you'll find a probability which is less than 5%. And also that gives you an evidence of rejecting the null hypothesis.
Oh, okay. So I could literally calculate. Okay, so I can calculate the z-score for my calculated z. I can go to the z table and figure out that's the probability of that number being where it is. Like that's the probability of it happening on a curve.
Yeah.
And then I can find the value for everything less than 5% also on the table.
Yes.
And then that's how I compare it. It just clicked for me, Victor.
Yeah. And to answer your original question,
Yeah.
if that's a t-test, the distribution is way different, but the principle is the same. So also on the t-table, because the t-table, the parameters is not like if I have a z-score, I can find a percentage. No, but in the t-test, you also need to know degrees of freedom. So basically, when degrees of freedom is different, you get a different distribution. The shape is a little bit different. It depends on your degrees of freedom. So it's the same. And what I always do is first, I need to calculate the critical t. So basically, this is a z-test, a critical z, but in the t-test, I need to find a critical t. How to do that? I plug in the percentage, which is in most cases 5% or 2.5% in a two-tailed test. Then I plug in my degrees of freedom, which in most cases n minus 1. And I can get my t-score instead of a z-score. I get my t critical value. And then by the same token, I calculate my calculated t. This is my t calculated. Calculated t. As long as it's greater than this t critical value, I reject the null hypothesis. It's the principle is really the same compared with the z-score test.
Yeah, that makes a lot more sense. So let me just clarify one thing. So essentially the t value is always going to be, or not the t, let's do the z. The z on any curve for anything, the z critical value, that's not what we call it, but you know what I mean, is going to be the same.
It's going to be the same.
Every problem.
Yes.
It's the calculated z that we find, that we look up ourselves, that will change.
Yes.
So like if I'm always testing against 0.05, like I'm always going to use 1.97 versus 1.9.
If that's a one-tailed test. And again, if that's a two-tailed test, you find
right. And then you cut it in half, right?
Yeah.
Okay. That makes so much more sense to me.
Yeah.
But So, but basically we're testing, it's all probability. Okay, I'm getting it.
Yeah, because the area of the whole distribution is 1. So we can
Yeah.
use the area to determine the probability.
Okay. That makes a lot of sense. Okay. I'm following T and Z.
Okay.
So thank you. That was really, really helpful. So now the P's. What is the difference between like all these P hats and P's and like
So
how is this?
the P is a percentage. I just calculated. This is a P value. Basically,
So like
you reject the null hypothesis if your calculated P is less than 5%. Then you
okay.
reject the null hypothesis. It's really the same. So all of those are related.
So why are we going from I think if for the z-score originally we were using like x's and mu and things. Why are we going to p's now?
The P is just probability, right? The one way you reject the null hypothesis in a t-score test is that the z critical value is less than your calculated t, right? A second way is P less than 5%. It's just like what I just told you. Like you
Yeah.
plug in your z-score into that table, you can find a percentage. That percentage is your p-value. P-value is just stands for probability value. Um,
Okay.
so as I said, if you find a z equals to 2, it's greater than 1.96, right? So you'll probably find a p which is around 4, maybe 4.9%. This is the p-value of your z-score test. As
So what
long
I
as
was
it's
telling
less,
you
yeah, as long as it's less than alpha, you reject the null hypothesis.
and being less than like the actual 5%.
Yeah, alpha is,
So,
it depends on which alpha you choose, right? If you choose a 5% alpha, but it's a two-tailed test, then you have
right.
to make your p-value less than 2.5% in order to reject the null.
Okay. So for p-value, wait. But you find the p-value in the z test, correct?
Yeah,
So
that's really
that
the same. In the t-test, you can still find a p-value.
but why do we call it a critical t value or t critical value then?
The p-value is a probability. Um, so
So that's what you were saying is at the center of the chart. So then the t critical value is what you wait, what? Hold on. So the
basically,
t
a t-test is pretty much very similar. Basically, one way is you can find a t-critical value, but here, instead of two parameters, like you have to find two parameters instead of one to get a t-critical value. The first is the degrees of freedom, and the
yeah.
second one is the alpha you need, right?
Mm-hmm.
Many cases is 5%. That means like the area on the right here is 5%. It's
Mm-hmm.
0.05. This is the area. So here you find your t-critical value. That gives so the t critical value gives you the cutoff point of 5%. And if your
Okay.
calculated t, here is your calculated t, is greater than the t critical value, then you reject the null hypothesis, right? Because the
Okay.
area is less than 5%. That means the null hypothesis being true is less than 5%, and you reject the null hypothesis. The p-value is just the area here. This is a p-value.
Okay.
It's really similar to the z-score test.
I see. Okay.
So basically, there's two ways. For example, if t critical value is less than t, you reject the null hypothesis. If p-value is less than 5%, you reject the null hypothesis, and they are actually the same.
Okay. Let me just write this down. I see it. Okay. This makes a lot of sense now.
Yeah.
So my last question on TZPs and all these. When do you know to use the t-test versus the Z?
Okay. So so
Because I imagine that like on the
yeah.
final, they get just figure this out. And I'm like, I'm not going to be able to tell like when I do what.
So
Because last
basically,
night, Professor
okay.
Bartman, let me tell you what he told us last night. He said, use, hold on, wait, where is it written down? If, no, hold on, wait, where did I write it? He basically said for large samples, use the Z, and for small samples, use T. Where is this written? Yeah, that's what he told us.
Okay, so in this class, a very important characteristics is as long as you have a binomial distribution, you use Z.
Okay. How do I know it's binomial just looking at it though?
Yeah, you should look. So what is some characteristics of a binomial model? First, the probability stays the same. So basically, tossing a coin is a binomial model.
Okay, I see what
The
you mean.
the probability stays the same. Like the first, like if I get even if I get 9 consecutive heads in a sequence, that doesn't change the probability of the 10th toss. The probability stays the same. And also, there's only 2 possible outcomes, and their probability adds up to 1. So that is basically a binomial distribution. So
Okay.
if I ask you what is the probability, like the first example I gave, the probability of getting 600 heads out of 1,000 tosses, then you
Mhm.
use a z-score test because that's a
Okay,
binomial distribution,
got it.
and also the sample is very large.
Okay.
But I think like the most important characteristics is it's a binomial distribution. And speaking of the sample size, many times as long as it's greater than 30, we can use the z-score test. That's a conclusion by the central limit theorem.
Okay.
And for t-test, I mean, most of the time, first the sample size is like much smaller. That is true. And the second one, like a lot of times you're doing a 2 sample t-test instead of a 1 sample.
Yeah.
So as long as you see like 2 statistics, 2 sample, and then you have to do a t-test.
Okay.
And another like important thing is in the z-test, your formula is more like x minus mu
Yeah.
divided by the standard deviation, no matter what is this. So the standard deviation of the number or standard deviation of a probability. But in the t-test, it's more like x minus mu divided by the standard error or the
Yeah.
pooled standard deviation. The pooled standard deviation is like really difficult to calculate. The formula is very long. Sometimes it's
Yeah.
a standard error. It's like standard deviation divided by n, the square root.
Hmm.
So basically, this is a standard formula for z-score test, and this is for t-score test. So if you have like a large number in this, so like for a binomial distribution, this standard deviation from binomial is NPQ square root,
Yep.
right? So you have a standard deviation here, and you can calculate. But in a t-test, sometimes the only way is you calculate the standard deviation first, and then you divide it by n and square root. So basically, the formula is a little bit different.
Okay. Okay. I got it, I think. So basically, if I read the problem and I'm trying to decide whether it's a Z or a T, kind
Yes,
of, if I can
yes,
determine that it's a binomial, that's how I should make my decision first.
yes. So
Okay.
in the homework problem of like last week, there is like if that the cream will like increase your like skin,
Yeah.
so something that is a that is actually a binomial, right? Because there's 2 outcomes, increase or not increase. and the probability, I guess, is like 0.6 something. Is something
Yeah.
you want to test. That is a binomial model. So you
Yeah.
will use the
Okay.
Z-score test.
Okay. So then what is the P versus the P? The P hat is like the sample, is the sample mean, right?
You can use whatever notation,
Oh,
I
you can do
guess.
whatever you want. Okay.
Yeah, so basically you're just so basically this is things you have to test, and
Yep.
then you have an actual P. It's the P
Yep.
you observe. I don't know how, like, it's P hat or P not hat. I don't like
Okay.
I don't care about like those notations, but you have an
Okay.
actual probability that you find, which is you can calculate doing from that graph in the homework problem graph. Is like a
Mhm.
number of cases your skin. I don't know if it's your skin quality increased divided by all of the people. So that is your actual observed P. And that 0.06 is the probability that you want to test if that is true. In other words, that's the null hypothesis.
Okay. So, and then you want to test the observed one. So that means when you calculate the standard error, you're using the observed P.
Yes.
Okay. I'll write that down.
That is also a z-test, and um,
Okay.
so the x minus mu is this stuff minus 0.6. This is your x minus mu. But here the standard deviation instead of NPQ, I guess it's PQ divided by N. I think this is a standard deviation for the probability, right?
What, that's PQ over N square root?
Yeah,
Okay.
that's the standard deviation in that problem. This is like NPQ. You just
Okay.
need to remember two things. So basically, NPQ is a standard deviation for the number observed. Like here I have like I want to test 0.6 probability, right? If I find 10 people, then the
Mm-hmm.
number observed, the expected number observed is 6, right? And this
Mm-hmm.
6, this is a mean, and it have a standard deviation, which is NPQ, which is 10 times 0.6 times 0.4 and square root.
Okay.
But again, this 0.6, this probability itself has a standard deviation, and you use PQ divided by N square root, which is, but here you don't use this P, you use, maybe this is P hat, this is your observed one. So you use P hat times 1 minus P hat divided by N and square root. That is your standard deviation.
Okay. So this P 1 minus P over N square root, that's the standard deviation essentially of a probability.
Yes.
Okay. That
And
was
you
my other
find
question.
this number would be much less than if you
Yeah.
calculate that using the NPQ, because like the standard deviation, like to explain that in natural language, is just a fluctuation between the mean, like on the right side, left side of the mean. So here the
Mm-hmm.
standard deviation of the observed number is 6 plus or minus some fluctuation. This fluctuation could be like a little bit larger than this 0.6 plus or minus to a fluctuation. So this number would absolutely be smaller, much more smaller than here, this um,
Okay.
standard deviation. Yeah.
That makes sense. That actually makes a lot of sense. Okay. Okay. Let me think what else I was thinking of. Like the homework, I just feel like I wasn't getting it, but like I understood, I get the calculations. It's just like interpreting them was hard, but this is like super helpful. Um, Yeah, I could like redo this homework and probably get it all right now.
Yeah, I didn't look at like this week's homework. So
Oh,
basically, I'm like looking at every week's homework on like Saturday night, and then I had the office hour Sunday morning.
oh God. That's horrible. Am I gonna fail this class, Victor?
No, no. I think nobody fails this class.
I was gonna say, like, there's no way I can fail. Like, I'm putting in so much work to this class, and
Yeah,
I'm still not
definitely.
doing well. What'd you say?
I mean, definitely, nobody fails this class as long
Okay.
as you are putting some efforts in it.
I'm putting in a lot of effort. I just want you to know that. My last question,
Okay.
that I still don't really understand on the homework. On part C, I followed along in your office hours with Grace, and you did like that factorial. I forget what it's called already, but it's the n factorial, n minus x factorial, x factorial.
Yeah.
How do you know to do that?
Oh, so that question. Basically, you can use a z-score test to answer that question. Because
So
I
you
said
could.
so I said so first it's a binomial, right?
Yep.
Okay, your null hypothesis is there's equal chance to find a positives or negative. That is absolutely the binomial. The probability it's just like toes and coins. The probability doesn't change. There's only
Mhm.
two outcomes. The only problem is the sample size is not big enough. I guess there's only 15 or something, 15 sample size maybe.
Yeah.
Like you just observed 15 positives or negative. It's smaller than 30. Um, Remember like the toes and coins example I gave you, like there's what is the
Yeah.
probability of getting 600 heads out of 1000 toes?
Mhm.
You can use the z-score to calculate that probability. But you can use another formula to calculate this probability. If you remember, it's 1000, choose 600. It's the
Mhm.
materials you learn like in first few weeks,
Right.
times zero point 0.5, the probability
Mhm.
of getting a hat, to 600, times probability of getting a tail, zero point 0.5, to the probability to 400. Remember this formula?
Yes.
This will actually give you a p-value. This is your p-value.
So
So
that's
what
just
we
the probability.
what we are doing is we use the z-score test to approximate the binomial distribution. So when z-score test is used, we're actually using a normal distribution, right? You know that the z-score distribution, this is a bell curve. This is just a normal distribution, right?
Mhm.
But in reality, I have a binomial distribution. So the thing is, as long as I find more than 30 observations, then my observed statistics are very similar to a normal distribution. That is a conclusion by the central limit theorem. So basically, I'm using a z-score test to approximate this, because
Okay.
this is not practical to do. Even if you use a computer, it takes I guess a few seconds to calculate this.
Mhm.
What's that, by the way? 1000 choose 600 is 1000 factorial divided by 600 factorial times 400 factorial. Right? You can look that up. This formula. It's in the slides in the
Yep.
first few weeks. This is not doing 1000 factorials. You're gonna like 1000 times 999 times 998 all the way to 1. It's very complicated to do. So what we're gonna do is we use a z-score test to approximate that. You get a very similar p-value.
Got it.
For the
So,
homeworks, like for part C, you can use so basically you can use a z-score test, and I'm not gonna like punish that. Even though the sample size is not large, the problem is it's not that good to approximate a binomial. using a normal distribution because the sample size is not large enough. But you can do that. You can use a
So,
t-test. You can use a z-score test.
okay. So like officially you're not supposed to because the rule is it has to be a sample size of 30.
Yes.
So, but this factorial equation, which I don't remember what it's called, but I remember the equation, the formula. Essentially, when you're done, you're getting the probability, you're getting the same thing that you would get from doing a z-score. Like this probability is what you would
It's
essentially
even
get
more
for
precise
that.
probability because you're
Okay.
using like very precise math to calculate that. And so for part C, what I anticipate is actually you use a very precise math, a very precise formula to do that. So basically that is a question of so I have 15, I discovered 15 observations. So if I get 7 positives and 8 negatives, I'm not surprised at all. And I think,
Yeah.
oh, maybe their probability is just 50% for like for positives or negative. But in that question, basically I discovered 13 positives and 2 negatives. Then that's a hint that maybe this 50% is not true. So what I'm going to do is it's like very similar to I'm tossing 15 coins and I get 13 positives and 2 negatives. Then I have to be skeptical that this coin is not a fair coin. So I just calculate what's the probability of getting more than 13 heads out of 15 toes using a similar formula. It's just like 15 choose 13 times 0.5 to 13 times 0.5 to 2. I just use this formula, and that is my p-value. And this is a very precise p-value of what is the probability of observing more than 13 positives among 15.
Got it.
This p-value is absolutely greater, less than 5%, less than 5%. So that's why I reject the null hypothesis. I would say this is not a fair coin.
Got it.
The probability of positives and negatives are not 50%. But you can try, actually you can try. You use those two different methods. You can use a z-score test. And then you can use the p, the precise p, and you will find they are both essentially zero. They're both very, very small, but they're different because here it's not really good to use the like a normal distribution to approximate binomial. But again, it's so low, so both method works.
Okay, that makes a lot of sense. Actually brings it like full circle now.
Yeah.
Okay. I think that's it. I know this was like it was ZT tests for dummies, but I truly just it was not clicking for me. But I get it now. Thank you,
Yes,
Victor.
I try to like get some in-person review session before the finals, something like
Wait, say that again?
I mean, I'll try to like schedule some like maybe in-person review session before
Oh,
finals.
I know. No, I have already been thinking about that, Victor. Like I need to start studying now.
Yeah.
I need to like last night in class, professor was like going through what we're gonna like learn next.
Yep.
And I just could not believe that there was still more to learn. It was like I can't retain anything else. I haven't taken a math class in so long. I don't even remember what it was like.
Yeah, it makes sense. But like I think like it's the hardest class during your MBA journey. So don't panic.
I was gonna say, do you TA for any other stats classes or math classes?
I didn't TA, but like I took a lot of them.
Okay.
Yeah, and I also like viewed some schedule of the MBA students, and basically the other class are like more like practical based. That you know a lot of like communication, you know a lot of marketing stuff or finance, those things, marketing, especially the management. Those are more like practical based. You do a lot of like case study and
Yeah.
a lot of presentation. Basically, you're trying to figure out a real life problem.
Yeah.
But this class is very, very theoretically based. So yeah, I know it's hard.
Are you a business major? Because you're undergrad,
Yeah,
right? You said?
yes, I'm a business major.
Okay. But you're just really good at math.
Yeah,
Oh man. Wait, what year are you in?
the third year.
Okay. Okay. All right. Well, thank you, Victor. But I am like, I have to like go through everything myself and figure out what I need review sessions on. So if you're okay with having just these, just me, I will schedule more. Do you get paid for these?
I get paid for the TA stuff, definitely, but not too
Not if-
much.
So not if I like for this hour, you won't get paid.
Oh no.
Oh shit. I'm sorry. I just
But
wasted an hour.
it's fine. It's fine. Like that's a job I have to.
Okay.
I have
I'll
to make sure like
consolidate
nobody
everything.
feels the cost.
Oh yeah, that's true. If I might be the one, but I've already like rationalized it in my head. If I fail this, it's not a big deal. Okay. All right, Victor. Thank you so much. I really, really appreciate it. I'll talk to you later. I'll see you on Sunday.
Okay, see you. Have a good night.
Okay, thanks. Bye. You too.
Bye.